I'm going to continue my exploration of chain sliding off the table. So in this case, we're going to do a chain sliding off the table, but with friction. So previously I did a video, I'll link to it down below, right over here. Everyone always points, so I feel like I have to point in YouTube. And I did it in a couple of different ways, but I did find that the acceleration of a chain depends on the length of a chain, or how much is hanging over the edge. And I got this expression where s double dot's the second derivative of s, and s is my position. So that's from before. I got that. But now what if there's friction? So what would we do in this case? And I'm going to use the half Atwood machine approach again, but let's just start from scratch and do the whole thing. So let's just say I have a coefficient of friction of mu k, coefficient of static friction mu sub s, and then I'm going to say that the friction force, the static friction force, is less than or equal to the coefficient times the normal force, and then for kinetic friction it's equal to the coefficient times normal force. These are pretty normal models for friction. So let's just get right to it. So I'm going to break this into a half Atwood machine. So in a half Atwood machine I have mass m1 up here connected by a massless string to another mass m2. And in this case, this piece is mass 1, mass 2, and this piece of the chain is mass 2. So let's just go ahead and say, I used this before, I'm going to define the linear density as the total mass m divided by the length of the chain L. So that means up here I can get, if this is a distance s, then the mass m2 is going to be s times lambda, which is going to be m over L. And then m1 is going to be equal to this length, which is going to be L minus s. So it's going to be L minus s times the density m over L. Okay, now we do have a little bit of an issue here. I'm going to do this in a short way. I have a problem on the motion of a half Atwood machine, a normal one, with friction, and I'll link that down below. But you see the problem here is as this thing moves, then these masses are not going to stay the same. This mass is going to increase and that mass is going to decrease. But still, I can treat this as one system. And so on this system, I have a gravitational force, m2g, pulling down, and then I have a frictional force, F friction, pulling back. And then the whole thing moves with an acceleration. So I can say F net equals ma, and the net force, and let's say it's accelerating this way, so the net force is going to be m2g minus the friction force equals ma. Okay, now this friction force depends on, let's say, if I do have a gravitational force pulling down, and I do have a normal force pulling up, and those have to balance because the box doesn't accelerate up or down. So that means that the normal force N is equal to m1g, and the frictional force, I'm assuming it's sliding right now, and I'll get to what do we have to do to make it slide in just a second. Let's assume it's already sliding. So then I have the friction force, F, just friction, is equal to mu k for kinetic friction times m1g. So if I put this all together, I get m2g minus mu k m1g equals m total, that's the total mass that accelerates. The whole thing accelerates, right? This force and that force combined together accelerate the whole system. And yeah, you could separate this into two pieces and calculate the tension and then get two equations, two unknowns, but that's not what I want to do here. If you want that, go down to this video. So I want the acceleration. So A equals, now I'm going to put in my values for M2 and M1. So I get, and I'm going to, let's just divide this. Let's do it right here. So let's just say M2G minus over M minus mu K M1G over M. Now I'll put that in the next page. So I have A equals let me just rewrite that. M2g over m, where m is the total mass, minus mu k m1g over m. Okay. Now I can put in my expression for m2 and m1. So this is going to be s m over g over m L. Because the m2 is sm over L, and the mass cancels. And then minus mu k, and that's m1 is going to be L minus s m over L. And then I had over m. So these masses cancel. So I get A equals S G over L minus mu K L minus S over L. Okay, let's stop for a second. Could we simplify? I could multiply this out and I'll just get a mu K, which is kind of weird. There should be a G up here. There's a G. There's a G. Okay. Yeah, because that has to have units. This has units of acceleration, meters per second squared, distance over distance. No units, distance over distance, meters per second squared. So that's good. Okay, let's stop for a second. If mu is equal to 0, then this term goes away and I get back to what I had before. That's a good thing. Okay. I'm trying to think. The mass does indeed cancel. Is it worth it? I think it might be worth it. Let's just write this as Sg over L. And now I'm going to multiply this out. So I have minus mu k Lg over L plus mu k Sg over L. Does that help? Those L's cancel. Well, then I have a constant term, and these two terms I could combine. So let's say A equals S times G over L plus mu K G over L minus mu kg. And this is kind of interesting because I get, again, the acceleration is proportional to the position. But this constant here is greater than g over L, but then you have to subtract off this other constant over here. So that's just really interesting. I guess you could get a negative acceleration. If s is really small and it's moving, it would slow down and stop. Right? I'm trying to think if I want to solve this. I think I'll just solve this numerically instead of doing it algebraically, because this constant term in there does make it a little more complicated. You have to do a change of variables. I think you do a change of variables to solve this, and I don't want to do that right now. Okay, but that's the acceleration. I'm pretty happy with that. I'm going to switch to Python. Don't worry about that. Okay, but now, what if what if it doesn't even start to move, right? So let's go back over here. This is M1, and that's M2. And so on this mass, I have M1G, I have N, then I have the frictional force, FF, and then I have the tension. And this one I have tension, and then M2G. And I've left off the vector signs because it's kind of a weird situation where things are moving in really just one dimension. So let's say this is at rest, and I want it, if I have a small amount of mass right here, then the tension in the string is going to be equal to the gravitational force, and that's going to be this tension. So as long as that's less than this, it's not going to move. So how much do I have to have hanging over the table for it to move? Well, so I want to look at when the tension is equal to the maximum frictional force. So for this mass right here, it's not going to be accelerating, which is kind of weird. because once it accelerates, then the tension will decrease. That's kind of weird. Well, let's just set it up and see. Okay, so I'm going to say maximum friction is F friction is equal to the coefficient of static friction times the normal force. And that's going to be the coefficient of static friction times m1g. And I want that equal to this weight over here, m2g. So I can solve the g's cancel, and I get mu s m1 equals m2. That's what's going to happen in order for it to slide. Now let me put in my values for m1 and m2. So I get mu s equals times L minus S times m over L equals S times m over L. And that cancels. So I get mu S times L minus S equals S. So if I multiply that out and I add mu S to both sides, I get mu SL equals S times mu S plus 1. So S equals mu SL over mu S plus 1. That's the amount that has to hang over for it to start sliding. I kind of want to do this experimentally now, right? Because I could measure these coefficients of friction and see if this is actually true. But let's just see if this makes sense. Is S going to be less than L? Well, I have a coefficient less than 1, and I'm dividing by something greater than 1, so yeah, it should be less than L. Let's pick some values and then do this numerically and see what happens for this situation. Okay, so let's say L equals 1. M, which I don't think I actually need, equals 100 grams, so 0.1 meters, kilograms. The coefficient of static friction, I'm going to say, is 0.3. The coefficient of kinetic friction is 0.2. I'm just picking those. Okay. And then, so here's what I'm going to do, just a reminder for the numerical model. Once I have the acceleration, I'm going to say that's the change in velocity over the change in time, which is v2 minus v1 over delta t. If I solve that for v2, I get v2 equals v1 plus a delta t. So this is my velocity update formula. If delta t is really small, then even though the acceleration is changing, I can calculate the new velocity. So I'm going to calculate the acceleration based on my equation right here first, and then use that to update the velocity. And then I can say the average velocity is approximately equal to v2, which is delta s over delta t, which is s2 minus s1 over delta t. If I solve this for s2, I get s2 equals s1 plus v2 delta t. That's my position update formula. And then I just update time, t2 equals t1 plus delta t, and then do it all over again. That's my recipe for numerical calculation. So I'm going to do this, and I'm going to compare it with, I'm going to have both models. I'm going to use my model from before using the no friction case, and then compare that right next to with friction, and we can see what happens. So I'm going to switch over to Python, so I'll see you over there. So this is my old program. I'm just going to start with this, right? Because why reinvent stuff? Anyway, I'm going to use this along with the other calculation too. So let me just copy this, and we'll call it table chain with friction. No, not friction. Friction. There we go. Save it. So now I need to add in here a couple of things. I need the coefficient of kinetic friction. I'll call it UK equals, what did I say it was? I wrote that down somewhere. I said it would be 0.2. 0.2, and the static friction US is 0.3. I already have the length. The mass doesn't matter, so I don't need that. Okay, now I'm going to use, let's go up here and put some labels. Let's leave F1. Let's use F2. F2 is label frictionless. and this other one label friction, just so we can tell them apart. So blue is friction, red is frictionless. So down here, I need two variables, right? So I'm going to be doing it twice. And so I have S and S2. I'm going to let S2 be the frictionless one. So I already started off with S1. And I'm just going to jump into, I guess I should calculate S min equals the minimum distance I calculated as US. I think I should call these mu S, mu K, mu. So this is from my calculation. It's mu S times L divided by mu S plus 1. That's the minimum. And let's just set S equal to that. S equals S min. And S2 I calculate. And that's called that S0 equals S min. I know that's dumb. But you do dumb things sometimes, and that's okay. Okay, down here I have, this is the accelerator. See, this line right here is the exact solution for the frictionless change. So I can just leave that as it is. Now over here, I'm going to type in my expression for the acceleration. It was S times G divided by L plus mu K times G divided by L. All of that minus mu K times G. And then the velocity that's the same. This is the same. I think everything else is the same. I think this is going to work. And I'll just leave this as, let's just not print this stuff. I can calculate that, but it doesn't really matter. Okay, let's see if this works. If this works, I'm going to be pretty impressed with myself and with you for sticking to it. Oh, okay. Let's see what we got here. So this, the frictionless one, and friction. Okay, I'm pretty happy. That seems like it's legitimate. One thing that you're going to notice is that I should change this to while S2, because I have the chain that without friction is going to fall off first. And so, oh, I didn't define it yet. That's why. So just copy this, put it right there, and then run it. Okay. I guess it didn't really make that much of a difference. But the, and now let's, the thing that we can always check, which we kind of already did, but what if the coefficient of kinetic friction is equal to 0? So what if it's 0? So if let's multiply this by 0, and then those two lines should overlap again. Yeah, good. That works. Okay, now let's try something. What if I start off with S0 as something really small? So let's say S min, let's do it right here. I'm just guessing S min equals 0.01. What's going to happen? Okay, excellent. Ooh, it actually went backwards. Okay, so in this case, the chain does not fall off the table and it goes backwards, because you got to realize I put in there an expression for the friction is pulling it opposite. But if it stopped and the friction is pulling opposite, it's actually going to accelerate it backwards, and that wouldn't really happen. So really, your model for friction, I assumed the direction, and if the direction's 0, then it doesn't work. So you can fix that. And I'm gonna stop here because I think I've got this working. I'm gonna stop here, and this is a great homework assignment for you. See if you can make this chain work so that you can give it an initial condition and it either sits there and doesn't move, or it moves with friction, or if it starts with an initial velocity and it's slowing down, what would happen then? Actually, I'm pretty curious. You'd have to have only a tiny little bit. Ooh, what about one that you push and it's a little bit hanging over the table? You push it and it's slowing down, but then as more and more chain gets over the table, it starts speeding up. Oh, I want to do that one. Okay, I'm going to have to think about this. I'm going to make it as another video, but I think I'll just stop right here. I'll give you the code for this, so save it, and I'll share the link down below, and I'll put the other videos in there too. I'm going to add one more video to do this pushing chain thing. But really, I think I might go and skip to the two-dimensional chain first. Because remember, this is the chain that can only go down after it goes off the table. I want one that can fly off the table too. And so that's the one I'm going to do next. But I got to do a little bit of work for that. I want to show you how to do lists. We're going to have to do lists and functions before. So I might make a video on lists, and I might make a video on functions. All right. I'll see you guys later.